Hello math students, today's video is 3.3 all about behavior. In 3.2 we talked about what happens to various functions when you get close to positive infinity and when you get close to negative infinity. We're going to continue talking about this today, but we're going to specifically look at the graphs of the functions. So for the first part of 3.3, we are going to use a graphing calculator to look at the graphs of various polynomials or other functions, identify the degree and leading coefficient for the polynomials, and then state the end behavior. So number one is one that's pretty easy to do without a calculator. It's just a line with y-intercept at 3 and a slope of 2. So maybe it looks like that. Remember in 3.2, we discussed that the degree is the biggest exponent. There's not an exponent on the x here, which means that there's a 1. So the degree of this polynomial is a 1. The leading coefficient is the coefficient of the term with the biggest exponent. So I'm just looking at that first piece. So my leading coefficient here is a 2. This next part down here, this is what is called the end behavior. This is really what's going on the ends of the graphs. This top part right here, so the arrow means approaches. So anytime you see an arrow, replace that with the word approaches. So I'm saying as x approaches positive infinity, or as x is going to the right, I want to know what is f of x doing. So on this graph, as I go to the right, I'm going up. So I would say f of x approaches positive infinity. On the bottom, when it says x approaches negative infinity, f of x approaches something, this is talking about the left side of the graph. So as my graph goes to the left, it is going down. So I would put a negative infinity. On number 2, this is one where I am wanting to use some sort of graphing calculator, whether I use an actual graphing calculator or a graphing calculator app such as Desmos. So when I put it into graphing calculator, this approximately is what my graph looks like. I'm not too picky about what the middle of the graph looks like at this point. I am just worrying about the ends. Before we get to the end behavior, the degree and leading coefficient. Degree is the biggest exponent. Leading coefficient is the number in front of that piece. So I don't care about anything except for this x cubed. So the degree is a 3. The leading coefficient is that 1. When I do the end behavior, so I'm saying as x approaches positive infinity, or as I'm going to the right, f of x approaches, I'm going to say positive infinity because my graph is going up. And then as x approaches negative infinity or moves to the left, f of x approaches negative infinity or goes down. We're going to continue doing the same thing for number 3 through 4. This is what the graph of number 3 approximately looks like. Once again, I'm not being super picky about the middle section, but I want to make sure the ends are going the right direction. To identify the degree and leading coefficient, I'm just going to look at this first piece right here. The degree is the exponent. Leading coefficient is the number in front of the x. For the end behavior, I'm going to look on the right. It's going down, left, goes up. So I'd say as f of x, or as x approaches positive infinity, f of x approaches negative infinity. And as x approaches negative infinity, f of x approaches infinity. This is approximately what the graph of number 4 looks like. For the degree and leading coefficient, once again, I'm just going to look at the first piece of the polynomial. My degree is a 4. Leading coefficient is a 1. As my graph goes to the right, it's going up. To the left, it's also going up. So I would say as x approaches positive infinity, f of x approaches positive infinity. As x approaches negative infinity, f of x approaches negative infinity. Number 5 is a little bit different because it is not a polynomial, it is a log. If you remember what log 2 of x looks like from module 2, it goes something kind of like this. So I don't have any negative end behavior, but I can say as x approaches positive infinity, f of x approaches positive infinity. If I wanted to do a left-hand end behavior, I could write something like as x approaches 0, f of x approaches negative infinity. But my graph never goes to the left of 0. When I graph number 6, it goes something like that. To find the degree on this one, because it's in factored form, I'm just going to look and see how many x's do I have. If I was to expand this out, there's 2 x's, so my degree is 2. Leading coefficient is going to be that negative 2. End behavior, my graph goes down to the right and down to the left. So I'm going to say as x approaches positive infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches negative infinity. Number 7, once again, is not a polynomial. Square root graph looks something like that. So it doesn't have any left end behavior, so I'm not going to worry about that. On the right, it is going up, so I'm going to say as x approaches positive infinity, f of x approaches positive infinity. The graph of number 8 looks something kind of like this. To find the degree, once again, I'm just going to see how many x's do I have. There are 3 x's, so I'm going to say my degree is 3, and then my leading coefficient is also a 3. It's that 3 out front. As I go to the right, my graph goes up, left, it goes down. So I'm going to say as x approaches positive infinity, f of x approaches positive infinity. As x approaches negative infinity, f of x approaches negative infinity. This next section is pretty much the same thing except for I'm already giving you the graphs and I want you to just tell me the end behavior. So I'm going to see what happens as I go to the right and the left. On number 9, the right goes up, left goes down. And then I'm going to write out the entire end behavior, not just fill in the blank. So I'm going to say as x approaches positive infinity, f of x approaches positive infinity. As x approaches negative infinity, f of x approaches negative infinity. Number 10, as I go to the right, it's going up, left goes down. So as x approaches positive infinity, f of x approaches positive infinity. As x approaches negative infinity, f of x approaches negative infinity. Whenever you're writing end behavior, this part is always going to stay the same. The only thing that changes is this last little piece over here. Number 11, as I'm going to the right, my graph is going up. But when I'm going to the left, it's not going up or down. It's actually just approaching 0. So when I write the end behavior, I would say as x approaches positive infinity, f of x approaches positive infinity. But as x approaches negative infinity, f of x approaches 0. Number 12 goes down to the right, down to the left. x approaches positive infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches negative infinity. Number 13 is up to the right, down to the left. X approaches positive infinity, f of x approaches positive infinity. X approaches negative infinity, f of x approaches negative infinity. Number 14 is I'm going to the right. This is similar to the other exponential one we had. As I'm going to the right, it's approaching 0. As I go to the left, it approaches positive infinity. So as x approaches positive infinity, f of x approaches 0. As x approaches negative infinity, f of x approaches positive infinity. Number 15 is asking questions about 2 and 3. It wants to know which of these has the greatest value as x approaches positive infinity. As I'm going to the right on number 2, my graph becomes more and more positive. As I go to the right on number 3, my graph is becoming more and more negative. They both have the same degree, but because number 2 is positive, that means that it has the greatest value as x approaches positive infinity. On number 16, it's asking me to compare number 5 and number 11. So number 5 was log base 2 of x. Number 11 was an exponential function. It's actually y equals 2 to the x. So it's wanting to know which has the greatest value as x approaches positive infinity. Both 5 and 6 are increasing as I go to the right. They both approach positive infinity. But number 11 is exponential, which is the inverse of the log. Exponential functions grow a lot faster than log, so I'm going to say number 11 has the greatest value. Number 17 wants me to compare number 2 and number 4, which has the highest degree. It's going to be number 4. Number 4, the degree is 4. And then number 18 wants me to compare 11 and 13. It wants to know which grows faster as x approaches positive infinity. This one's a little bit tricky because number 13, at least initially, is growing faster than number 11. But number 11 ends up growing faster because it's exponential. So number 13 starts faster, but number 11 ends faster. So the last thing we're going to look at for this video is we're going to talk about how I can identify the end behavior without even having to look at a graph. If I just give you an equation, how can I identify end behavior? There are two things that we need in order to do this. We need to know what is the degree and what is the leading coefficient. So the leading coefficient, this tells me what happens on the right side of the graph. The degree tells me on the left. If I have a positive leading coefficient, that means my graph is going up to the right. If I have a negative leading coefficient, that means my graph is going down to the right. If I was to write this in the arrow with the arrows, positive leading coefficient as x approaches positive infinity, f of x approaches positive infinity. Same thing down here. Negative leading coefficient as x approaches positive infinity, f of x approaches negative infinity. And then it's the same thing down here. The degree once again tells me the left side of the graph. If I have an odd degree, so if the biggest exponent is an odd number, that means the left and the right sides are opposite. This is like a line. It either goes from the bottom left to the top right, or from the top left to the bottom right. Even degree, that means that the left and the right sides are the same. They go in the same direction. So this is like a quadratic. We either have a parabola that opens up, so the left and right sides both go up, or a parabola that opens down. The left and right sides both go down. So to finish filling this out, positive leading coefficient with odd degree means I am going to go down as I go to the left. This is kind of like a line that has a negative slope. A positive slope. If I have a negative leading coefficient with an odd degree, this is like having a line with a negative slope. So as I am coming from the left, I am positive. Even degree with a positive leading coefficient, this is like a parabola that opens up. Both the left and right sides are going up. Even degree with a negative leading coefficient, this is like a parabola that opens down. Both the left and right sides are going down.